One more time. Actually, it's this weekend. Yeah.
I thought we were going to call it Sept.
Katie Status. Katie Green. I'll make sure you get all the Katie Catherine's. All right, some quick reminders before we go ahead and get started. That you have homework due on Friday. Chapter 2 homework is due Friday. There will be a group quiz on Friday. The groups that you picked out, I guess last week, if you forget who you picked, I'll have that written out. Or if you didn't pick a group, I put you in one. And then there will be an individual quiz Monday. Good there? Any surprises? All right. Okay, so let's get started on Chapter 4, which is our chapter on protein structures. Yeah.
Should we have the amino acids and functional groups memorized for Friday?
No, not yet. When you get through Chapter 4, then I'll have you memorize them for sure. Because we're going to hit some important things in this chapter, and so you get like another week and a half. Yay! Yeah, be able to identify the R group or the whole thing I'll put together. Know the, like glycine is also the same as GLY. And then there's a one-letter initial for each one, which is on the back cover of your textbook. So glycine is also known as G. And for the most part, they all make sense. Glycine is G and methionine is M. There's some funky ones. Good on that? All right. Then let's talk about proteins and protein structure and why this is an area that we really need to spend a lot of time talking about. All right, so proteins are the basis of stability in the cell. They give the cell structure. They are the workhorses. They transmit information. And so they do a bunch of different jobs. So they are used for structure. They're also used as molecular machinery, and we'll look at some proteins, I think, in next chapter, like actin and myosin, that actually move. And because they're able to put themselves into motion, they're able to do some really fascinating things in your cell. And then they're also used for expression of genetic information. So some questions we're going to want to ask as we look at proteins and protein structure. That's not spelled right at all. Dictates. Too many C's. What dictates protein's 3D structure? What forces stabilize this 3D structure? And then finally, another big question is going to be which functional groups in the protein allow it to interact with other proteins. All right, so we're going to be able to answer all those questions by the end of the chapter, hopefully. So we're going to work through some of the very basics of amino acids. So amino acids, right, there's your 20 standard amino acids that you guys are in the process of learning all about, or just refreshing yourself. I'm sure you guys already had it in the bag, just looking at it over again, just to, you know, make sure that you got it right. Alpha amino acids, with the exception of proline, which I will get to in a second, are called, let's see, I left off part of the sentence. Alpha amino acids, with the exception of proline, are called alpha amino acids because they all have a primary amino group and a carboxylic acid group on the same carbon. So the question that threw most people on their homework is, what is special about that carbon? It is chiral. That is a chiral carbon. So what does it mean to be chiral? It's attached to 4 different things, and then we can give it 2 designations, right? What are the 2? We can give it R and S, right? So because this is a chiral center, I could designate it, depending on what this R group is, an R or an S. And that'll be true for all the amino acids except for proline. Proline has a different shape that, does anyone know off the top of their head what proline looks like? Right, so proline, make sure I get it right. If I didn't have it in my notes, proline. Looks like this guy. So that alpha carbon is no longer acting the same as it is up here. It's now part of a ring, and so it doesn't have the same R and S designation as the other amino acids. So it's kind of a funky guy, which we'll get to later, because he can cause a lot of trouble, depending on what your protein is. So we'll come back and spend some time talking about him.
So all other do not have a chiral center?
They don't all have chiral centers, they all have an alpha carbon.
Okay.
So, like, glycine. Right, that one is a standard amino acid. It has an alpha carbon because it has an amino group and a carboxylic acid group, but it's not chiral.
Okay.
Right, because it has only 3 different functional groups attached to it. It is really sweaty in here today. All right, so the 20 standard amino acids fall into 3 main categories. With respect to their R group. The R group is either going to be hydrophobic, polar, or charged. So let's take a look at those 3 different categories. All right, so hydrophobic amino acids. Have non-polar side chains, or R groups. If they are non-polar R groups, how do those R groups interact with water? Strongly or weakly? Weakly, mm-hmm. So as I'm putting together my protein and starting to fold it up, am I going to want to put those hydrophobic groups on the inside where they interact with each other, or on the outside where they're interacting with the water? Inside. So these amino acids are typically found on the inside of a protein. We'll do a little activity in here on Friday where you get to build your own protein, and we'll practice folding it to get your amino acids either on the inside or the outside. All right, charged amino acids. What property do you think all these amino acids have in common?
Charge.
They all have charge. They have a permanent charge at physiological pH. I would have said physiological, but I don't know how to spell it. PS, Y, ecological, ends with an L for sure. Body pH. If they are permanently charged, do they interact with the water strongly or weakly? Strongly. How do they interact with each other, strongly or weakly? I'm going to say it depends, right? If you got 2 negatively charged amino acids, they're going to be repulsive and not associate. But if you got 2 of the opposite charge, that'll be a strong association. So the association with each other is going to vary depending on what 2 amino acids you're looking at. All right, my polar amino acids. These have side chains or R groups that interact with water because they possess hydrogen bonding ability. So would these polar amino acids be on the outside or the inside? Probably on the outside. Can I rule out them being on the inside? No. So there's a possibility they'll be found on the inside, either interacting with a charged one or with another polar molecule. So I'm going to flip this over so I can draw a little picture. So still looking at polar. So depending on the presence of nearby amino acids, these polar amino acids can become ionized. So what does it mean if the amino acid is becoming ionized? It's getting a charge. It'll become charged, become an ion. So the best example of this is histidine. Oh, that's clearly not right, but there's too many H's in there. That's why. Ignore this. Let me try again. Forgot it. CH. That looks better. Is histidine chiral? Yes, it is also chiral. Not a trick question. Just this is histidine, yeah. So this is histidine in its neutral state, right? It's both positive and negative, right? But overall, it doesn't have any charge. In the presence of donor protons, I did not leave myself enough space, sorry. This nitrogen can become charged. So histidine has the unique property of being able to act as an acid or a base, because it can either accept a proton going this way, or it can donate a proton going that way. So histidine is going to be one of our unique amino acids that has a lot of different properties depending on its what the other amino acids around it are. Good. Everybody's almost all caught up sketching it. Questions? Okay. All right, so those are going to be our 3 categories of amino acids. So let's talk about how these amino acids become proteins. So, alpha amino acids polymerize through the elimination of water, and we can use that reaction to make dipeptides, tripeptides, or polypeptides. If it's a dipeptide, how many amino acids are participating? 2. Excellent. What if I wanted to make a tripeptide? How many amino acids are participating? 3. Just checking. Very good. So far, everyone's passed. And if it's a polypeptide, it is more than 3. So if I have my amino acids, 2 amino acids, 2 generic amino acids. So my 2 generic amino acids. And I'm going to do a condensation reaction, or a elimination of water reaction. Can everybody read that? A little faint, sorry. That's a little better. So a condensation reaction is an elimination of water reaction. And what we're going to do is we are going to make a new bond between this end of the first peptide and that end of the second peptide to make a new dipeptide.
You say R1?
Yeah, sorry, just saying they're 2 different
Oh, okay.
R groups. They could be the same R group. So this bond right here between this carboxylic, what was this carboxylic acid and what was the amine, this guy right here is now called our peptide bond. By convention, so when you're talking to other biochemists out and about on the town, by convention, we will always draw it the same way. We'll always have the amino group on the left, we'll always have the carboxylic acid group to the right. And because there's always going to be an amino group on the left, we call that the N-terminus. Any guesses on what terminus is fancy English for? End, yes. Oh, question?
Yes.
Yeah.
On the carboxylic acid end, is that still a double bond to oxygen?
Here?
Yeah.
Yes. Yeah. Sorry, they kind of skipped for me. There we go. So any guesses on what this end is called? The C-terminus. Mm-hmm. So then the properties of this new dipeptide I have made come from these 2, in this case, 2 R groups. I don't know where to write that. I'll put it up here. Right, so here I have my peptide, and the only two things that really are going to affect what makes this protein different than any other protein and how they interact with another protein are having those R groups sticking out on the edge. Because all proteins will all have an N terminus, they'll all have a C terminus, they'll all have peptide bonds, so the only thing that makes them different for these.
If you just try one amino acid, it wouldn't matter like where you put amino.
If it's just one, no.
Okay.
I think the textbook will still draw it with the N to the left and the carboxylic acid to the right. But
Okay.
questions on drawing my polypeptides? Okay. In that case, let's talk about everybody's favorite topic in organic chemistry, which was pKa's. I'm imagining that groaning's actually excitement, like you can't hold it inside. You're like, ooh, so excited. No, is that not what that sound was? All right, pKa values are determined by induction and resonance. Remember those words from organic chemistry, induction, resonance structures? Everyone's blanked out that entire year of their life, for the most part. Okay. Well, if it was physics, that would make sense, but organic chemistry, yay. No? Mm-hmm. All right, this table is in your textbook. It is, let's see if I can find it real quick. You'll need this table to do the homework due in 2 weeks. So that's your table 1-4 from your Pratt and Cornley textbook. So pKa values are determined by induction and resonance. So let me draw 2 different amino acids and we'll talk about how we can tell the pKa's of them, and then we'll do some practice problems. So let's say I have So I have those 2 amino acids. So aspartic acid and glutamic acid. Okay. Looking at the functional groups on both of these, they're the same, right? Except for this one CH2 group. This one's slightly longer than this one. Is the amine going to withdraw electron density or donate electron density? So if it has a positive charge, does it want more electrons or does it want to give even more away to become more positive? It wants them, right? The NH3 is a positively charged, so these guys are both electron withdrawing groups. So it's withdrawing electrons both from this guy up here and from this guy down here, right? Pulling electrons from both ends of the amino acid. Which one of these 2 acids does the amine group have a better chance of pulling electrons from both ends? Aspartic. Why aspartic? It's closer, right? In terms of distance, it is only 1 carbon, well, I guess 2 carbons away from this group. This is 3 carbons away, so it can pull more electron density from this one than that one. So if that is the case, if this amine and the aspartic acid can draw more electron density because it's closer to both of the carboxylic acid groups overall, is this then a more or less stable structure than glutamic acid in terms of keeping its charge the way it is? It's more stable because it's able to withdraw all the electrons it wants to. It doesn't have to get protons or electrons from anybody else. I see some confusion. Let's see if I can write that out more coherently. Because our carboxylic acid group is close to the amine, it's more resonance stable, right? Because you're only one carbon away, so you can share those electrons back and forth easier. So it's more stable. So since it is more stable, the way it is it a strong acid, like it takes a very low pH to protonate these, or is it a weak acid where I can use a high pH? It is a strong acid. I just need to throw this marker away. I guess stronger. Is a stronger acid than glutamic because it's happy the way it is. It takes a lower pH to protonate these. So its pKa is 3.6. So when I say its pKa is 3.6, what does that mean in terms of pH? At pH 3.6, what happens? Or at pH 3.2? It gets protonated, it becomes neutral. Oh, yeah, sorry. So that is the pKa. So that's the acid point at which if you below that, there's tons of protons available in your solution, right? Low pH means lots of protons. There's lots of protons. Below 3.6, I can now protonate that. Okay. Let me write the pKa for this one. If this has a pKa of 4.3, why does that make this a weaker acid? Right. I can be at a higher pH for it to gain or lose protons, depending on which way you're looking at going. So at pH 4.3, below that becomes protonated, but above that it's deprotonated. So it takes less concentration of protons to protonate, which means it is a weaker acid. Okay, why don't we do a little bit of practice looking at this table, this pKa table, and predicting net charge. So these are pKa's of different amino acids or their functional group, right? So the C-terminus at pH below 3.5, this is deprotonated. At pH above 3.5, it is protonated. At pH 3.9, above 3.9, it is protonated. Below 3.9, it's sorry, messed it up. That's the wrong way. Above 3.9, it is deprotonated. Below, it is deprotonated. Yeah?
Is that for all of them?
It's for all of them. So at 4.1, if I'm above it, it becomes O-. If I'm below it, it gets protonated.
And were those numbers the PK values or the PK?
Say that again?
What are those values?
These are PKA's value. These are all PKA's. Yeah,
Can you say that one more time? So
Yeah.
above the PKA is chemical?
I'll just go ahead and write it down.
Sorry.
No, you're good. You're good. So given, we'll pick a PKA off the other side. We'll say the C terminus. Right, so if that's what I have off the table, right, 3.5 pKa equals that. If I am at pH 2, what does that say about the proton concentration in my solution, ignoring everything up here? There is a ton of protons, right? pH 2. Right, so there's lots of protons. So if I am at pH 2.0, is this group going to be protonated or deprotonated? Protonated. Why is it going to be protonated? Because there's tons of protons available for it to protonate it. Okay, so let's say now I am increasing the pH. Now I'm at 3.4. Is it going to be O minus or OH? So is it above or below my pKa? Below. I'm below my pKa, so it has to be OH. So now I'm at pH 3.6. Is it going to be protonated or charged? Charged. Or deprotonated, whichever one makes more sense, deprotonated. So that is the magic tipping point. So pKa's are the tipping point at which it either is always protonated or it's always deprotonated. So let's look at some ionization. So this is just one. Oh yeah, question.
What if the pH was exactly 3.5?
Then it's in equilibrium with its acid-base form. So there'd be equal parts, right, it'd be switching back and forth, equal parts protonated, deprotonated. So. It'd be in equilibrium with itself. All right, so then let's take a look at some practice problems, putting it all together. All right, so you'll need your pKa table, at least where you can see it, or you can see my pKa table. So ionization properties of amino acids. Is looking at the pKa, right? The pKa of individual amino acids. We'll determine the overall charge of a single amino acid, but rarely are we interested in a single amino acid all hanging out by itself. We are interested in chains, which you can't see. Here we go. Chains of amino acids. So let's look at a polypeptide chain that contains aspartame, tyrosine, glutamine, and cysteine. And I'm at pH 7. So I'm going to redraw this right underneath it. Actually, Actually, I'll just do this. Right, so I have the amine end, my 1, 2, 3, 4, 5 amino acids, then my carboxylic acid end in shorthand. So what I want you to do is we'll make a little table. Group in charge. All right, so I didn't leave myself enough space. So the group's moving along my polypeptide from left to right. I have an N-terminal, aspartame, tyrosine, glutamate, cysteine, my carboxylic acid end. So I write all those down in my groups. So then I am now at pH 7. So I want to go back to my table 4.1 from your textbook. And look at each one of these and figure out if it's going to be protonated or deprotonated. All right, so my N-terminus has a pKa of 9. N-terminus written in this way, NH3+. I'm at pH 7. It's going to be protonated because I am below pH 9, so NH3 is still protonated. If it is protonated, what charge do they have? -1, 0, +1. +1. Okay. Here I am looking at aspartame. The pKa of that is 3.9. I'm at pH 7. Is that going to be protonated or deprotonated? Deprotonated. Does that have a charge of +1, 0, -1? -1. So far, so good? Okay. Then I got my tyrosine. Tyrosine, in this way, tyrosine is written, does it have a charge? This R group of tyrosine, does it have a charge? No. If its pKa is 10 and I'm at 7, what does that mean? It is protonated. If it is protonated, what is its charge? 0. Right? Because it has that H on this oxygen, which means it is neutral. So I got 2 of those in a row, so 0, 0.
Can you say why again?
Sure. So the way it's written, it is neutral. And I am below, right, pH 7, means it is protonated because it's below that. And the protonated form of it is neutral, not charged. So if I was above pH 7, if I was at pH 12, this would then be CH2, benzene, O minus.
So it's just the neutral, like,
Right, its only choices are neutral and -1.
are there a lot like that?
I mean, like, cysteine would be another example where it's either going to be neutral or minus. Glutamate is neutral or minus. So there are some that are neutral or minus, or there's some that are plus to 0.
Which number again are you worried about being above and below?
This one.
Okay, so if it's above the pKa, it's deprotonated,
Yes.
and below it's protonated.
Yes. Yeah. What do you think, Megan?
So the structure that's drawn on the chart is the proteinated structure?
Yes. That is the protonated structure. Right, because I can't put an extra like this, OH2 plus craziness. Don't do that. It's like a rookie mistake. You guys are too smart for that. All right, so I just had this. Where is it? GLU. So if it has a pKa of 4, is it in, if I am above 4, I'm above 4, which means I'm deprotonated. Deprotonated makes this -1. All right, then let's look at cysteine. Cysteine, is it found neutral, +1, or -1? Neutral. If I am below the pKa, protonated, deprotonated. Protonated. If it is protonated, what is its charge? 0. Then the last thing is this C terminal. So its pKa is 3.5. So at pH 7, is it protonated or deprotonated? Deprotonated, so its charge is -1. Then the tough part, we add it all up. 0. Oh, -2. By tough part, I mean I already messed it up. -2. All right, and that is the end of class for today. So what I'm going to do is I'm going to send you home so you can work on this one, and we will pick up here on Friday. Yes, ma'am.
The next PowerPoint, can you make the text larger?
Yeah, sorry, I did it in the last chapter and I forgot to do it.